Now we are going to talk about kinetics. And today a little bit tackle behavior. Okay, so what does kinetics mean?
How fast?
How fast something happens, right? So usually in chemistry, we talk about two things being really important for how to understand chemical reactions, right? What are those two things? Thermodynamics and kinetics. And then if you're a chemical engineer, you have one more thing, which is what? You're designing a reactor, and you want to know how fast you can make something. What else do you have to think about? Transport, right? Transport. So chemists generally don't think about transport, but it's really important in electrochemistry, and it's really important in all practical chemistry because you've got to move species in and out, you've got to move products in, and remove reactants. And so that will come in here later, but primarily we're going to talk about what determines the rates of electrochemical reactions. So we can have O plus N electrons, and we can write a forward rate constant, call it Kf, to write a backwards rate constant, Kb, going to some species R. And what we want to do is we want to explain how Kf and Kb depend on the electropotential E. Okay, so we have an electrode, it has some electrons in it, and we had this simple picture, right? We had this very simple picture earlier that we have some Fermi level of the electrons in the electrode, and we can apply potential and move this level up and down as we form a double layer, right? And that if we, apply one potential, eventually electrons will go one way. If we apply the other potential, eventually, electrons will go the other way, depending on the relative position of these levels. But we didn't really articulate how fast those reactions will occur. And so this is what we're going to do quantitatively in this chapter. Articulate the rate of chemical reactions. And another thing I will note, if you remember in chapter 1 where we talked about mass transfer limited voltammetry, where we have a stirred cell with relatively fast mass transport and diffusion over this stagnant layer, right? And we calculate the shape of voltammograms, and you did this experiment in lab. You guys remember that still? And we write E. We wrote this all the time to derive everything there. The Nernst equation. What is this tell you? And what is the implicit assumption here? Fast electrokinetics. And why is that the implicit assumption? So basically what this is saying is the electrode potential and the concentrations at the surface, let's make this x equals 0, because then it holds at all times for our mass transfer limited case. The concentrations at the surface of the electrode determine the electrode potential, or another way to say that is these levels are always in equilibrium. And if they are in equilibrium, current is passed to get it to equilibrium. And that's why we calculated steady state voltammetry, where the change in the potential was sufficiently slow that this always held. And what we're going to do now is this is not going to be true anymore. It's going to be out of equilibrium, so there's going to be some, we call Q times an overpotential, eta. There's going to be some driving force to move, in this case, electrons from here to here, right? And we want to know how the current responds when this is not in equilibrium.
And that's material specific.
It's material specific, it's potential specific, it's electrolyte specific, it depends on a lot of things, and we'll go through that. So one basis for this in TAFL in 1905, very early electrochemist, looked at very simple reaction, hydrogen evolution. And what he noticed is if you plotted now, this is in the Texas Convention, if you plotted the current versus the applied potential, and we'll do versus standard hydrogen electrode, and you did this in acid, what you'd see is for platinum, it would look like this. So right at the standard potential, you'd start to get a lot of current for hydrogen, making hydrogen. But if you did something else, like nickel, nickel might look like this. Okay? So it's the same reaction, same thermodynamics, but one takes more free energy driving force to get the reaction to go than the other. So this has slower kinetics than platinum, right? And then you could keep going on, like gold, even worse, and then carbon, it's even worse. And that's in fact why carbon and gold electrodes are often used for electrochemistry in aqueous solutions. We say they have a very large overpotential. This is eta carbon, right? That potential there, that's the extra voltage relative to thermodynamic potential for hydrogen evolution that you need to drive the reaction at some current I. So the key is that different metals give different rates, and the surface affects reaction kinetics. Okay, so he recognized this experimental trend, and you can write an expression to fit this data, basically. And the reason you have this, actually, for these types of materials for this reaction, is the reaction actually happens in 2 steps. The first step, I think I may have showed you this before. You have an open side on a metal, plus a proton plus an electron goes to a metal hydride. And then the second step, there's a couple different second steps that can happen, but one of them is 2 metal hydrides goes to H2 plus 2M star. And so the energy of this bond determines the concentration of these MH species at the equilibrium potential, right? So the free energy of this thing determines these equilibria. So if this delta G is very negative, like if this is a very stable species, this reaction will be, it will be very much on that side, right? And this reaction will have will have less driving force for the second step. So what turns out is there's an optimal MH bond strength and rate. And there's sort of an optimal, and platinum sits right at the top for doing that reaction. It's almost thermoneutral, so each step has roughly the same delta G. And then Tappel said, well, I can write this phenomenologically, so I can write an equation for this. I equals A prime e to the eta over beta prime, where eta is overpotential. So basically all this is saying is these curves usually come up exponentially with applied potential. Do you know anything else that goes exponentially as you increase something? Rate constants go up exponentially with temperature. So one way to think about the overpotential, it's kind of like the driving force. It's in the same way that temperature gives you thermal energy to get over an activation barrier. Overpotential gives you electrical energy to get over an activation barrier. So they're kind of related in that way. Except in electrochemistry, we can nicely change the overpotential just by turning it on. We can change the driving force for the reaction. Okay, so how do we explain this? If you have an elementary reaction step, what's an elementary reaction step? Well, it's an equation that describes the physical process, underlying physical process, right? So you can't break it down into any more fundamental steps. So it's an elementary step. And this is a very simple one. A is going to B, right? It's super simple reaction. I can write the forward rate. What's the forward rate of reaction? Based on simple freshman kinetics, you learned it, right? Kf times what? Concentration A. So I'm going to write it differently. Ca, so it's consistent with the notes. And V back equals what? AB times C back, right? Or CD. Okay. And at equilibrium, what happens? basic stuff. What happens at equilibrium?
Yeah.
The rates are the same, right? So I can write KFCA minus KBCB equals 0, or KF over KB equals CB over CA, and we define this as the equilibrium constant. And we can define something called an exchange velocity. What does exchange velocity sound like to you? If this is a reaction velocity, what's the exchange velocity? Maybe like an equilibrium exchange velocity. So we can define it, V naught, V naught equals Kf at equilibrium, C concentration of A at equilibrium equals Kb concentration of B at equilibrium. So this is basically just a concept that even though the concentrations of A and B don't change at equilibrium, it doesn't mean the reaction stops, right? And in fact, thermal energy is driving it forward and driving it back at the same rate. Just what we wrote here, right? And so we can quantify that, right? And so if you have a reaction that's very fast, the exchange velocity is going to be very high. If a reaction is very slow, the exchange velocity is going to be very slow. So the exchange velocity kind of tells you how fast the system can get to equilibrium. If you start out with a system out of equilibrium, how long does it take? You mentioned the rate constant, any given rate constant, is related to temperature. I think. Do you guys remember how it's related to temperature? Experimentally, what is found? Okay, so you have some prefactor, right? E to negative EA over KT or RT, depending on the units, right? Let's use R because that's what we're going to keep it in molar. The only difference is molar or atomic units. EA over RT. And A is often thought about as an attempt frequency, right? So if you think about it, there's molecules randomly moving around, and there's some activation barrier you have to get over, and this kind of tells you what fraction of the collisions have enough energy to get over the activation barrier. This is thermal energy, right? Thermal energy. This is how often they collide, and that gives you some information about what the rate constant for the reaction is. And so it's, temperature activated. So we often see pictures like this, where this might be free energy, this might be reactant, this might be product, this is the so-called reaction coordinate. What is the reaction coordinate? So the way I like to think about it, imagine you have, a whole bunch of molecules. They can rotate, they can vibrate, they can translate. Those are all degrees of freedom, right? And we could, in fact, plot the energy of that system of molecules as a function of every single one of those degrees of freedom. Every bond angle, every bond distance, every position, and that would be an enormous plot, right? Because so many variables, so many degrees of freedom. But we could, in principle, make a multi-dimensional surface. Might have 100 dimensions in it, right? And every position on that surface has energy. And then I could say, okay, what's the easiest path to get from A to B, where all the atoms are arranged in arrangement A, and then all the atoms are arranged in arrangement B, and to get between those two, there's some barrier you have to get over in this multi-dimensional space. And what's the lowest energy path to take to get there? That's the reaction coordinate. And we're going to condense that down to one dimension that slices through those many-dimensional space, and that's the reaction coordinate. So we can think about this. Maybe it's like this, right? So this is products over here. Where's delta G here for the reaction? Okay, so this is delta G, right? Delta G a reaction. And we can just write it here. And so we can plot this here as delta G double dagger forward and delta G double dagger. So obviously, which rate constant is going to be bigger, the forward one or the reverse one? Forward, right? So if I put little marbles in this well and little marbles over there, and then I jiggle it, that's thermal energy. Are the marbles more likely to go this way or this way? More likely to go this way, right? So does that make sense? So is the net rate going to be forward or the net rate going to be backwards? Forward, because delta G is negative for this reaction, right? Delta G goes down. Products have a larger delta G than reactants, so therefore the delta G is negative. Spontaneous reaction, it goes downhill, forward rate is bigger than reverse rate. This is non-equilibrium, right? Okay, so this is kind of the picture we have. And so we can write this, right? KF, so we can do this expression, equals AF e to the negative delta G double dagger F over RT, and K back equals A back e to the negative delta G double dagger B over RT. Now the neat thing about electrochemistry is you can actually change, if your reactants involve an electron in an electrode, say an electron in platinum, if I apply potential to the platinum, I actually change the free energy of my reactants. So I can actually move this well up and down by applying a potential. So you can change the free energy of a reaction by applying a potential. And it's very hard to do in chemistry, because usually the free energies are given by energies of formation of the species, right? But in electrochemistry, we can do that. So that's very neat. We'll consider an electron. X equals 0. Through my electrode surface. I can have some concentration of O as a function of X and T. And so this is the concentration of species O in the reaction O plus electrons, and electrons goes to R, so it's concentration of oxidized species. And I can write the rate of the reaction, V forward, the reaction velocity, equals KF times concentration of O, 0T, equals IC over NFA. So this is going to be called the cathodic current. Cathodic means reduction. This is going to be the forward rate constant. And for this reaction, O plus an electron going to R. And this is at position 0, i.e. next to electron. And similarly, I can write the rate of the backwards reaction. What's the rate of the backwards reaction given by? Kb times Cr, where?
0.
At position 0, so we care about the stuff that's right next to the electrode where the electrons can transfer. We don't care about the stuff in the solution, far away. 0 as a function of time equals Ia, anodic, over NFA. So F is Faraday's constant, A is the electrode area, N is the number of electrons transferred. I guess I should put N here, sorry. We're still keeping it general. Okay, so I can do that. What's the units of these? So if I work this out, coulombs cancel, I get moles per second per centimeter squared. What things have units like this? What kind of quantity is this? It's a flux, right? It's a flux. So it's a flux of the stuff coming to the surface and reacting. So this is a flux. So we usually have, so like rates of reaction in homogeneous chemistry are usually molar per second. Like if you mix A and B together in solution. But because we're doing reactions at electrode surfaces, we write the reaction rates typically as a flux. It scales with the electrode area. Okay, so we're all done for today. I'm happy to answer any questions before you all leave. Next time we'll go on and watch the derive what's called the Butler-Volmer equation for electrokinetics. It's one of the foundational equations that describe how fast reactions go and how they depend on potential.